A golf ball is launched by the golfer with an initial velocity of 45 meters per second and 31 degrees of angle above the horizontal. Now the question is, you are asked to find the time of flight of the ball. This is in part A. Part B, what is the maximum height the ball will reach in its trajectory. Part C, the range by which the ball reach along the x-axis. And in part D, you are asked to write down the equation of trajectory from the given information. By following the strategy we have already adopted in previous sessions, we're going just to put in the information we had from the problem, where the initial velocity is 45 meters per second and the initial angle, the angle of projection, is 31 degrees above the horizontal. Then we choose the Cartesian coordinates as shown in the figure. The velocity component in its trajectory has two components, one along the x-axis and one along the y-axis. So we have to obtain this information, or we have to put it as an information by substituting these values into the relation of x component, that is v naught cosine theta naught. I'm going to get for the x component 38.57 meter per second, and for the y component, which is equal to v naught sine theta naught, we're going to get 23.17. These are the information we have in the problem. Again, we have to remind ourselves that the velocity along the x-axis, the component of v naught x, will remain constant during the whole drive, while the one along the y-axis obviously will change. Now we're going to get the time of flight by using the information we have, and we're going to find the time from the start of the projectile up to the maximum height, where this time actually is half the total time of the flight. And we'll use this equation, the velocity along the component along the y-axis equal v naught y minus half gt, and by substituting half the time of the whole flight, we're going to get the time from this equation, because we know v naught y, we just found it, and we know that vy at the top at the maximum height is equal to 0. So we just put all this information in, and then t as the total time of flight is obtained as 4.7 seconds. And again, we have to just put emphasis here on this value. This value, when it's substituted, is substituted on as half the total time of flight, because this is the time when the ball reaches the maximum height. To solve the problem in part B, that's finding the maximum height, we have to use the third kinematic equation, that is delta y equal the product of v naught y with the time, and minus half gt squared, and t sub h is the time for the projectile to reach the maximum height, which is considered as half the total time of flight. Well, the information we have v naught y as obtained before, it's 23.17 meter per second, and we have the time of flight 4.73. We divide that by 2 in order to get the time for the projectile at the maximum height. Then putting all these values into the above equation, we're going to get 27.1 meters. That is the maximum height. To get the horizontal distance in part C, we simply use the only equation along the y-axis, that's delta x equal v naught x times t, with v naught x known as given in the problem 38.57 meter per second, and by inserting that into the equation together with the time of flight which we obtained of 4.73 seconds, we're going to get delta x equal 1.82 meters. Noting that x naught is 0, that's why delta x here equals x. To find the equation of trajectory, we have to use the derived equation and insert in this equation the value of theta naught, and that is 31 degrees. So in order to get the equation of trajectory as requested, which is y equal 0.6x minus 3.29 x squared. Now we can use the equation of trajectory by substituting different values of x and get the corresponding values of y. And here we got this trajectory as shown in the figure.